Right, welcome everybody. It's my pleasure to welcome everyone here to the Museum of London for the Gresham lecture. For those of you who don't know me, I'm Chris Budd, the Gresham Professor of Geometry. And today I'm going to be telling you about mathematical materials. I should say, for those of you who want to leave early, I'm planning to finish this lecture exactly 34 seconds early. At least I think some of you in the audience will understand why. The rest of you might like to work out why I will finish 34 seconds early. Anyway, those of you who've been coming to my lectures up to now will know that I've been following a theme about the way that maths is important in the modern world. Looking at various bits of maths linked in with the government's 8 great technologies. And sixth on the list of the 8 great technologies is advanced materials. So what I wanted to do today was tell you a little bit about materials, about the way that maths is important in materials, and I'm afraid to say a little bit of my own research in the subject, because this is a subject I'm very, very interested in. So materials, very important. They are everywhere about us. I'm wearing quite a few at the moment. And in a sense, they define our civilization. When we're asked to think of history and classify history, we talk about the Stone Age, when we use stone as a material, and then the Bronze Age, and then the Iron Age. And now what are we now? The Composite Age or the Electronics Age or something like that. We've defined ourselves in terms of the materials that we use. So materials essentially divide into 2, well maybe 3. The most obvious being that the natural materials, these are what we used right from the dawnings of civilization. I've already mentioned rock, possibly the very first material anyone used, apart of course from fig leaves, is wood, and then you have ivory, bone, natural materials that come from animals, or things that you dig out of the ground, like the metals, or things like crystals and sand. So these are natural materials. And when you have a natural material, you've got what you've got. Okay, it doesn't have properties that you can change, but there are properties that you can learn to use. And of course, the reason we use wood is it's very strong and light. The reason we use metal is that it can take a sharp edge and you can cut things with it, and so on. So these are natural materials. Mathematics is very important in understanding how natural materials behave. But what has really defined mankind and made us somewhat sort of different from other animals is the materials, not so much that we have around us, but the ones that we have made and have produced, which wouldn't naturally exist. So there's lots of these around. One of the earliest manufactured materials is glass. Glass certainly goes back to the Egyptians, if not earlier. And glass is basically made by heating things like sand to a high temperature and then letting it cool. So you get this wonderful material, which of course we can use for many applications, such as windows and so on. Paper is one of my favourite materials, and we'll come back to paper at the end of this lecture. Our modern world is dominated by plastics, which are materials essentially made out of oil products. Cloth, which is made from a variety of things. And I think possibly one of the earliest man-made materials to be kind of recorded is bronze. It's there in the Bible. It talks about bronze swords and so on. And bronze was made by amalgamating copper and tin to produce something which was harder than either. And here's a lovely example of a bronze axe. And a lot of science goes into making bronze. You've got to get the temperatures pretty well right to do that. And later on we had steel. which takes iron, which is a kind of natural material, but adds the right amount of carbon to it to produce something which is, again, stronger than the original. We have nylon. Concrete certainly goes back to the Romans. And semi-conductors, which are the material that is at the very, very heart of the electronics industry, selenium, silicon, germanium, and so on. I'll talk about liquid crystals and composites as well. So these are the sort of artificial materials. So what's this got to do with maths? Well, maths can basically do two things, both of which are extremely important. Mathematics can be used and is used to understand the property of existing materials, to work out the best way to use a material so that it can do its job. So one of my areas of research, for example, is to help design aircraft wings, where we take materials but try to make the actual design of the wing as light as possible, but as strong as possible. Okay, and we use a lot of mathematics to do that. But also, mathematics is used in the design of things called metamaterials, which are materials where in advance you'd say, I want it to have certain properties which don't necessarily exist in nature or anything like that. And by using mathematics, you can then essentially design something which has the sort of structure that you want. Here's an example on the left. This is carbon fiber, which is a material made out of long strands of carbon amalgamated together. And carbon fiber is an extremely strong, extremely light material. It's used in aircraft. It's also used in the design of fishing rods. Okay, very long, very strong things, which otherwise you wouldn't have. Here's something on the right, which is rather fun. This is a material made out of lots of cogwheels, which has the property that you can squash it and it kind of uniformly squashes together. Normally when you squash something, it comes out another way, but this is something you can squash it all together, and this is something those of you who want to come to Bath Taps into Science, which is our science festival, Friday and Saturday this week, small advert there, can have a play with some of these things, which are very strange things. So this is the role of mathematics, and what I'm going to try to do today is take you through some examples of the way that maths is used. I better warn you, there are occasional bits of heavy-duty maths involving differential equations, because that's the nature of the beast, but I'll try to keep the heavy-duty stuff to a minimum and give you a flavour of how things are happening. But we're going to start with a little bit of self-indulgence, a subject of great interest to me, by looking at possibly one of the earliest materials used. I've said that wood is possibly the earliest material, and one of the problems with wood is that it doesn't last, but rock does, and one of the earliest building and tool materials is rock and stone. So if you go to Africa, stone tools going back 1 million years are actually fairly common. There's a lot of them out there, and you can find them on the ground. Tools which were used possibly over 1 million years ago, incredible span of time, by our earliest ancestors. And it was exploiting the properties of stone into making to tools, which again was a major part of the growth of the civilized world. Here we have the Egyptians, who constructed these extraordinary structures out of stone, which have lasted for several thousand years. Easter Island, and just down the road from me at Bath, we have Stonehenge, and again we have these wonderful structures which required a large amount of maths and engineering to put up. So one of the earliest materials that we have is rock. Now when we think of rock, our usual thought is that it's very, very strong, it's very, very solid, it doesn't change very much. Okay? And that's sort of true, but it's only half true. And something that I've got very interested over years is studying rock as a material and working with geologists to try to understand more about rock by learning a bit about the role that maths plays. And one of the more interesting things about rock is that its properties really depend upon how long you're prepared to look at it for. So with rock, a short time is about 10,000 years. Okay, a long time is 1,000,000 years, a very long time is 1,000,000,000 years. Rocks go back a long, long way, even though we've only been using them for a few thousand. And one of the most interesting properties of rock I like is that over a short time scale, rock is actually elastic. So elastic materials are very important. An elastic band is an elastic material. A wire is an elastic material. A spring and rubber is an elastic material. And what an elastic material is, from a mathematical point of view, is a material which has the property that the displacement that you get, the extension, is proportional to the force that you put on it. And rock behaves in that way over timescales between about a second and about 1,000 years, which I said was a fairly short time for a rock. Now, it's really nice to talk a bit about elastic materials, because one of the pioneers of elastic materials and one of the people that kind of did a lot of the original mathematical and scientific work on it was this chap, who is Robert Hooke. Robert Hooke lived, the dates here, 1635 to 1703. He was very much a contemporary of Newton. They very much did not get on. And one of the consequences of them not getting on is that I think the story is that Newton burnt most of the pictures of Robert Hooke. So this is kind of a guess as to what he looks like, but it must be right because it's hanging up in Gresham College. And Robert Hooke was one of my predecessors as Gresham Professor of Geometry, and therefore great to have him there. And what Hooke is very famous for is, well, one of the things he's very famous for is his work on elasticity. And in this picture in Gresham College, you can see he's holding in his left hand a spring. And again, I say a spring is a material which has the property that the displacement of the spring is proportional to the force acting on it. And that was a law that we believe was invented or discovered by Hooke himself. So it's very nice to put that into context. And if you actually visit Gresham College, you can see this picture, which is not a likeness, but is what we think he looked like, okay? Because, as I say, Isaac Newton did the dirty on him. But anyway, there's Robert Hooke and his law of elasticity. So rocks, as I say, behave as an elastic material over a short to medium time scales. And one of the consequences of that is that they have waves which go around the whole Earth following an earthquake. And these are elastic waves. So they are a force causing a displacement, and then that displacement travels as a wave, and it travels in one of three ways. It can travel over the surface, it can travel through the core itself, that's called a P wave, or it can travel in the mantle, and that's called an S wave. And earthquake waves are both good and bad. They are bad because they cause the earth to shake and buildings to fall down and people, unfortunately, to die. Here's a lovely thing. This is a jar which was found in China, and it has dragons here and frogs here, and the dragons have balls in their mouths, and when the wave hit the jar, the ball would fall into a frog's mouth, and by doing that you could work out where the earthquake was. So that's an early earthquake detector. here's a slightly more recent version using detecting these waves. So these are elastic waves. And one of the things that you can use these for is you can actually find the composition of the Earth by measuring the strength of the waves, and then you can kind of go backwards and work out how they're distorted, and actually that is used to determine the interior structure of the Earth. So that's why we know the Earth has a core, and the core is made of iron-nickel amalgam. Okay, so that's an elastic wave. And these are used a great deal nowadays by oil companies. They don't wait for an earthquake. Typically what they would do is they'd have a boat, and underneath the boat they would detonate a compressed air gun, and the air gun sends waves through the sea and then under the sea, and these are elastic waves which go through the rock, and they can bounce off things like oil and so on. And by measuring them back at the ship, you can then work out pretty accurately what's under the sea surface, and therefore work out where the oil is. Another outfit that uses sort of waves under the sea are whales and dolphins, and these boats have to watch out for the whales and the dolphins to make sure they don't detonate and kill the animals. And actually one of my jobs at Bath is to help them find where the whales and the dolphins are by essentially listening to the waves that they create under the sea. So one of the aspects of my work is that I am saving the whales, which is rather nice. Okay, so that's the kind of the elastic properties of rock as a material. If you wait for a bit longer, over a few millions of years, now admittedly we don't as people wait for millions of years, but to the Earth that's nothing. Rocks behave more in a what we call a viscoelastic way. And a viscous material, and we have lots and lots of these around in our houses, is a material where the velocity of the material, not the displacement, but the velocity, the speed of the material moving, is proportional to the force that you put on it. So a good example of that is treacle, or tomato ketchup if you prefer. So you put the tomato ketchup into the hole, and after a while it comes down. Lava coming out of a volcano like this, and toothpaste is an example of a viscous material. A viscoelastic material is something which has both viscous and elastic properties, and that's more like rock. And human flesh is a good example of such. Here's a fish. Anyone that came to my last lecture will remember that I got quite excited by dead fish. And one way you can test how fresh a fish is to see how elastic or viscous their skin is. And that allows us to determine whether we can eat it or not. So that's what a rock does. Why should we be interested in millions of years? The reason we're interested in millions of years is because underneath particularly underneath the sea, as continents meet each other, so you get huge forces coming up from the Earth, which push the plates together, and those plates then push the rock as though it was a material. Okay, imagine you have a lump of plasticine and you push it, so the plasticine distorts, and as you push on rock over a million years or several million years, so the rock distorts and you get shapes, and those shapes are what we call mountains, okay, or valleys, or all sorts of geographic features. And so by studying rock as a material and thinking of the shapes that it gives you, just as we might, as say at home, push on toothpaste or whatever, so that we can understand not only what the shapes mountains are like, but also, and this is very, very important for mining companies, we can understand what the rocks look like deep, deep down, and that helps the companies work out where to mine for other materials that we might want, such as minerals or indeed oil. So first mathematics coming up. If I take all of this stuff, the viscoelastic nonsense that I've spoken about, you can actually write down an equation for the way that rock as a material distorts over a period of about 5 or so million years under the sort of very, very high pressures that you get from continental drift and also the high temperatures that you get. And there it is. Isn't that beautiful? That's our U here, as I'm sure you appreciate, is the displacement of the rock. X is space. And these are numbers that come out of the kind of general properties of the rock. And P here, that's the really important thing, is the amount of pressure that you apply to the rock. This equation looks a bit scary, but actually engineers use this equation every day. One of the most important materials that is used all the time, was almost certainly used in this building, is a steel beam. A steel beam or even a concrete beam, reinforced concrete. Certainly in bridges or in steel reinforced buildings, a steel beam is one of the most important materials there is. And engineers have to know how strong a beam is and how well it will stand up to compressive forces and whether it will buckle under those compressive forces. And this equation here is used by engineers where it is called the beam equation in order to predict how safe a building or a bridge will be. So it's a very, very important equation. E here is the elastic modulus, and that is the number introduced by no less a man than Robert Hooke. So there's a bit of a Gresham link there. And I refers to the cross-section of the material. So this is a lovely equation, and you can apply it to rock. And if you apply it to rock, it predicts that you get patterns a little bit like this. And these are what, again, geologists recognize as the shapes that lead to things like mountains and stuff like that. So that's a very good equation. I say engineers use it a lot. It helps them understand how a beam deflects. But we realized a few years ago when studying rock, well, we, many others, that rock doesn't just behave like that. One of the key features of rock is it's what we call a layered material. So typical rocks are formed at the, under the sea over many, many millions, maybe billions of years as sediment accumulates. And it tends to accumulate in layers. So you get what we call a layered material. Other examples of layered materials, well, composite materials, the carbon fiber materials that are used in aircraft that I mentioned earlier are made up of lots of layers. And a book is made up of lots of layers of paper. So a telephone directory, if you want to kind of be strong and tear a telephone directory in half, you're working with a layered material. Inspired by this, at Bath we decided to study rock layers. We didn't have any rock available and we couldn't wait a million years. So we made some very good use of the fact that our business cards for our department had gone out of date because we changed the name of the department, and got a whole load of them and squashed them to pretend that they were rock. And you get these wonderful patterns with zigzags like this. These are caused by compressing this material and seeing how the layers interact with each other. It wasn't just for fun that we did this. We were working at the time quite closely with Airbus, and Airbus want to know how the new composite materials that they're using to build the wings of the latest generation of aircraft will stand up to compressive force, and the sort of patterns that you might get when they actually fail. And these are the patterns that you get. This one, by the way, we were rather proud. We entered it for a competition, and it won a competition for a kind of nice interface between art and science. There's this kind of picture. Do rocks look like this? Well, absolutely they do. One of the nicest things about living in the UK is that we have access to some of the best rocks in the world in terms of sheer looking at the shapes type thing. Here are some rocks in Cornwall. This is Bude, which is on the west coast of Cornwall. Well, it's northwest Cornwall. Bude actually is where my family name, Bud, actually comes from, so they theorise. And this is an example of a nice piece of mathematics where you have a smooth fold here, which deforms into a sharp fold here. And mathematically, that's given by a thing called the swallowtail caustic. We're able to mathematically describe that. If you go a bit further down the coast from Bude, you get to a place called Millock. And here are the rocks in Millock, which I think are gorgeous. If anyone says, show me an example of maths in your face where you can't miss it, there it is. Isn't it beautiful? Lovely zigzags, which are exactly the same as the shapes that you get in paper folding. And the reason you get zigzags is that if you want to fit one shape over another in such a way that they fit exactly together, there aren't many shapes that will do that, and the zigzag is one of those. So that shape is the same as that shape, is the same as that shape, and they just all fit into one another. And just to give you a bit of scale, this is one of my colleagues over here. There we are, who is now professor at University of Exeter. But that gives you a bit of scale for these ones. I do recommend you go to Millock. These are absolutely lovely rocks. Why should we, again, be interested in this? Well, if you want to make a quick buck, here is our folded rock again. And sometimes the shapes don't quite fit over each other. You get gaps in them, which we call voids. And mathematically, we can predict where those gaps are. And what happens in real rock layers is that the gaps fill up with water over millions of years. The water deposits minerals. And some of those minerals can be quite interesting minerals like gold. And so if you know where the voids are and drill for them, you can make yourself rich. Okay, so that's kind of important. And the aircraft people are very interested in voids because they represent possible places where you might get failure of the material. So there we are, an ancient material rock, but right up to the present day in terms of aircraft composites, and mathematics helps us understand it. So let's again really move forward. One of the things you can do with rock, as I said earlier, was that you can take sand and turn it into glass. And glass is extremely important nowadays in communication. Until about the 1950s, or maybe a little bit beyond, our communication was largely done through wire, copper wire. But the majority of high-speed communication now is done by lasers and going through glass, fibre optic cables. One of the reasons we do this is that a laser can convey much more information than an electrical impulse. And the second reason is that you tend to lose much less energy if you send light down a fibre optic cable than if you send it down an electrical cable. But you still lose energy, and until recently, if you had a long fibre optic cable, say underneath the ocean, you'd have to put booster stations in every so often, which would take the light and amplify it and then send it on. That was until mathematicians, working with physicists, working with engineers, had a look and realized that by using a bit of mathematics and some lovely geometry, it's possible to design a cable out of a special material, one of these famous metamaterials, which has the amazing property that it's almost loss-free, that you can send light down it without any real loss of energy. How's that done? Well, take one of these things, which are quite small already, and cut it through a section, and then do something to it, and you get a thing called a photonic crystal. So this is a photonic crystal, and what a photonic crystal is a essentially a long piece of glass, which this is a cross-section through it, with lots and lots and lots and lots of very carefully, what I will say drilled isn't quite the word, but manufactured holes. This isn't a material that you would ever easily find in nature. It's an example of a metamaterial, a material that's been designed from the outset with certain properties in mind, and those properties can be predicted through a mathematical analysis. Again, anyone that looks at that will immediately say, yes, you can see mathematics in that. What's going on here? Essentially, you shine light through here, and these things here all act as little resonators. They're all kind of singing to the tune of the light that you put in there. And those resonators have the property that they block any energy loss. There's no way energy can get out of there. There's a sort of subtle way that they do that. And so essentially these things are loss-free. You can put a pulse down the middle, it can go nowhere, and these holes here block the energy coming out, and so you can send information for vast distances without really any loss of energy at all. It's like having a wire with zero resistance. So these things are being used quite widely now. It's quite possible that a lot of if you have really high-speed broadband at home, that it might be carried through one of these. So where's the math in this? Well, again, another scary equation. This is the sort of equation that we end up solving to understand these things. It's an equation called the Helmholtz equation, which actually goes back to the 19th century. U here is the intensity of the light. X, Y, and Z are the three spatial coordinates. Omega here is the frequency of the laser light that you pass through. So that's the equation we have to solve, which isn't too hard an equation to solve in a simple geometry, but in a geometry like this is really rather difficult. And until fairly recently, people were trying to use supercomputers to solve this, and calculations were taking huge amounts of time. And then it was realized that you could exploit the properties of this material where you've got sort of what we call small scale, which is the holes, very, very small scale, which is the light, and what we call the macro scale, which is the whole crystal. And a big advance in recent mathematical techniques has been methods which can deal with materials which have several different scales, where what matters is the way those scales interact with each other. And we call these things multi-scale methods, and they're kind of becoming very important. And it was the kind of the simultaneous development of the multi-scale methods plus the means of manufacturing those crystals, which meant that we could get to these metamaterials, which are now so useful in our modern technology. As I say, the sixth government 8 great technologies is advanced materials, and photonic crystals is an important example of that. Nature's got in there earlier. Wood and bone both look a little bit like this if you cut them open. I had occasion just 2 weeks ago, if you've noticed I'm a bit wooden here, I unfortunately dislocated my elbow and had a good look at the bones in my arm when they did the x-rays, so I could admire what a wonderful material bone is. Wood itself is an amazing material because it's essentially got a very fine structure, and we're using multi-scale methods to understand these. We're using the same sort of methods to understand things like climate and weather, where you have lots of processes going on at different scales, and you can also use them in things like Wi-Fi systems, again, where you have lots of different scales interacting. I'll come back much more to multi-scale methods next year when we look at some more applications of mathematics in modern technology. So another area where we see mathematics playing a huge role in modern materials is a thing called a liquid crystal. So what's a liquid crystal? Well, at school you learn that there are various states of matter. You learn there are solids, there's liquids, there's gases. Later on you might learn that a plasma is another state of matter. But there are really other types of states of matter, and a state of matter which plays a very important role in modern technology is a thing called a liquid crystal. So what's a liquid crystal? Well, a liquid crystal is something which is sort of somewhere between a liquid and a solid. We'll see another example of this in a minute. It's a material which is somewhere between a liquid and a solid. What you have in a liquid is lots of molecules here all jiggering around at random, basically doing their thing, but keeping sort of vaguely close to each other. That's why that's different from a liquid from a gas. In a solid, like a crystal, and we'll look at crystals in a second, the molecules are solid, they're rigidly aligned in one direction but can't move around. What you have in a liquid crystal, and there are various states depending on the temperatures, you have what we call a nematic crystal or a lamellar crystal, are molecules which can move around like a liquid but like to align themselves in a certain direction like a solid. Okay. So we call these anisotropic because they have a preferred direction, but unlike a solid, they can change their direction. Okay, so that's what a liquid crystal is, and the direction of the molecules depends upon a number of things, like the electric field or the magnetic field, or possibly the temperature. So that's a liquid crystal. Why are they important? Well, liquid crystals are important because the displays that we have almost everywhere, so the display in a modern TV screen, which used to be a cathode ray tube, which was a big thing with vacuum and so on, is really cumbersome, has been replaced by a much slimmer thing, which is made out of these liquid crystals. The first, I think, the time they were used widely was when digital watches came along in the 1970s. And what happens in a liquid crystal display is, as I say, the molecules like to align themselves in a direction which depends upon, say, the electric field. And what you can do is shine light through these things and change the alignment of the molecules by passing electric field through them, and that allows you to change the display from, say, transparent to opaque, and that's why you can then display the numbers. One of the reasons liquid crystal displays were used for digital watches and became very popular is that they require almost no energy. The original things that we used for digital watches are called light-emitting diodes, or LED displays, which would require a lot of energy and would use up the batteries in the watch pretty quickly. But a liquid crystal requires almost no energy. And it's because it's what we call a bistable material. So the alignment of the molecules has two preferred directions, and each direction is very stable. Once it's in it, it'll stay in it and nothing matters. And the only energy required is not to give you the display, but to change the display. So in a watch, you'll be displaying it, changing it, say, once every second or so. So that's called a bistable system. It exists in one or two stable states, and energy is only needed to change between the states. And these are properties which mathematics predicted essentially in advance of the kind of physics. And the way it works is that liquid crystals can be defined in terms of the energy of the states, and typical energy as a function of, in this case, electric field, has this kind of a W shape where 1 and 3 represent stable states of the thing, and once the ball's sort of there, it will stay there forever, and then you give it a nudge to move it through 2, and you nudge over and you can stay down there. And the mathematics kind of predicted that this energy would look like this, and that allowed liquid crystals to kind of be designed and is still being used to help us in this huge industry of displays. One of the latest developments, I better warn you, is liquid crystal display clothing. The idea being that we can walk around in the clothing and we go to a party and we found somebody else has got the same coloured dress as we have or same coloured shirt, and so you just press a little button and instantly your dress or shirt will change colour to change for the party, or indeed if you want you can get it to advertise slogans or have Gresham College across it or whatever moving around. So this is a new development which we're going to be seeing in the future. Liquid crystals, I can't wait. Okay, so liquid crystals are an example of a crystal type material, and crystals themselves again have played as materials a very important part again in human civilization. Some of the earliest crystals, things like diamonds or other gemstones, of course go back forever in terms of natural materials that were used to enhance beauty and so on. In modern technology, crystals play an extremely important role in, say, a watch or a computer, in that they act as a device to control the frequency of that, say, the computer or the mobile phone. So a crystal is used, to govern the frequency so that we know everything is being transmitted at the right frequency. Crystals have a beautiful mathematical form. Chemists have long understood this and long exploited the properties of the mathematics of the crystal. And here's a lovely example. This is the buckyball, which is an example of a large molecule of carbon, which is made up of 60 carbon atoms arranged rather wonderfully in the shape of a soccer ball. So you have pentagons here and hexagons all stuck together to form a shape which is a truncated icosahedron. You see the same shape, sort of same shape in viruses. And the reason you get these wonderful shapes which kind of have a beauty all of their own right is because they, just like our liquid crystals, have energy states which are very stable, and the stable energy states are ones which have lots and lots of symmetry, and symmetry and beauty go very, very well together. So here's a nice example, and by using mathematics you can learn a lot about the properties of this material without ever having to go into experiments. Experiments are still very important, but you can learn things like its resonant frequencies and so on. So very, very important role. Crystals are also important. Here's in other contexts, this is a thing called a polycrystal. This is more like what you'd get in a typical metal, or especially a metal alloy, where you have a regular arrangement of atoms, but then you've got these lines here, and things fit together in different ways. And the properties of such an alloy depends as well as the arrangement of the molecules here, but also how what they call these dislocations link together. Another example is this is a rather beautiful picture, which looks like modern art, is an example of a material with two phases. Lots of things have two phases. Water and ice mixing has two phases. And again, lots of materials have this sort of thing. And mathematically, we can study these using fairly scary equations. So I'm going to put up the most scary equation of all. This is a thing called the Carne Hilliard. This is what I spend my life looking at. Isn't that sad? But this equation here, C here, in this picture here, if C equals -1, it's purple. If C equals 1, it's red. And if it's between purple and red, then it's between -1 and 1. And that shape can actually be described and understood in terms of this wonderful thing, which is called the Carne Hilliard equation, named after two mathematicians, Carne and Hilliard, who worked on it together. So this looks rather scary, and many mathematicians spend a lot of their lives studying equations like this. Why do they study them? Because they're important in understanding polymers and complex fluids, and polymers and stuff like that are vital, again, to modern technology. Our plastics and so on are all essentially polymers. They can be studied using this equation, and this is a powerfully important equation in industry to help us understand how these materials work and to predict their behaviour. So that's kind of the most heavy-duty maths I'm going to put up, and as I say, seriously important things can be found by studying that thing. Okay, so the next material I want to talk about takes me back to my previous lecture, which is granular materials. What's a granular material? Well, the clue is in the title. A granular material is a material made up of grains. What's made up of grains? Well, grain. Here is a picture of, I spent a lot of my life in Canada, of some grain silos in Canada storing grain. If you put grain into a silo, it's kind of important that you can get it out again, and you don't just put it in and hope for the best. You have to put grain into a silo carefully so that you can extract it, and so it flows out without jamming. And granular materials are materials in mixtures of grains, and they themselves have properties a little bit like liquid crystals, in that the behaviour of a material made up of grains depends upon how much energy there is in the system. So if you take a material made up of grains and just leave it by itself, it's quite likely that it will jam and not flow very much. If, however, you agitate it, so you shake it a bit, then it can start to flow much more like a liquid. And that's really, really important in the food industry for transporting granular things around, and important in other applications as well. Let's show some examples of materials which are made up of grains. Well, going right back to one of the earliest materials that we looked at, which is sand. It's made up of grains. When you pile sand in a pile, you get shapes which are particular shapes, and we need to understand those shapes and how stable they are in order to be able to both extract the sand and also to make sure it's safe. Very sadly, 50 years ago last year, there was a disaster at Aberfan when a soil heap collapsed on a school, and one of the reasons that collapsed was that not enough thought had been put into how you pile things up to make sure that they don't fall down again. So understanding that's very, very important. Grains are also important in the food industry with things like coffee. It's important in the pharmaceutical industry in terms of drugs and so on. And here we have a very interesting granular material, namely snow. And snow can change from being like a liquid, a solid, which is kind of how you want it, to being much more like a liquid with an avalanche, depending upon how much energy there is in the system. So mathematics can be used very usefully to predict and help design safe ways of transporting, moving, storing, and otherwise dealing with materials which are made out of grains. So give you an example of this. So every morning I come down in the morning, and the first thing I do, of course, is feed the dog. And after I've fed the dog, I have some breakfast. And I typically like breakfast which looks a bit like this. And I like cereal. And I don't know how many of you have ever had muesli or something like that. But when you find a box of muesli, you find rather strangely that at the top of the muesli are all the big nuts, and down underneath are all the small things. And it's rather paradoxical that the big things are at the top and the small things are at the bottom. And here's an example. There's all the nuts in my muesli. That was taken a few days ago, my breakfast. That shows you that materials which are made up of grains can somehow behave in a contradictory way to things which are not made up of grains. This is the Brazil nut effect. What's going on in the Brazil nut effect? Well, when you've got your cereal in a box, as it's transported to your house, however it's transported, it's typically shaken a lot. And when you shake a material, here's a material with lots of small grains with a big thing in it. There's the nut like this. As you shake it, everything moves up and down. And the more energy you put into it, the more it moves up and down. And when the big things move up, the small things go underneath because they can move more easily than the big things. And as you shake it a bit more, they go in underneath again. As you shake it a bit more, they go in underneath again. And eventually, the big things rise to the top. So in a granular material, big things rise and small things fall. I suggest that you do this at home with your next packet of muesli and actually do a bit of science, and you'll see that the big things really do move to the top and the small things really do go to the bottom. And understanding things like this are important is actually quite important in an avalanche, because one of the consequences of this is that if you kind of, in an avalanche, try to stay still, there's a reasonable chance you will float to the top because the sand will go underneath you as it agitates. Almost the worst thing you can do is to waggle around, because that will prevent the snow from accumulating underneath. But there's lots of other things you should be doing in an avalanche, like not being in it in the first place as well. Okay, my penultimate material I want to just, as a bit of a joke, but it's rather fun, is to ask, is the Harry Potter cloak possible? Anyone who's been to Harry Potter films will know that he has this cloak of invisibility which he puts on, which renders him invisible. And for many years it was thought that this might not be possible. We now think it actually might be possible. And scientists have been working on it, and this is called the Rochester cloak. And here's an example. There's a team at Rochester in the US, University of Rochester, who have developed a material. If you put your hand in front, you can actually see through it. It's beginning to look possible that the Harry Potter cloak might actually become viable. This is kind of how it sort of works. You have a material. This is an example using mirrors, where there's a potato, where light comes in, bounces off that mirror, that one, that one, that one. And so if you look in front, what you see is what started there, back there. That's a thing which would render the potato invisible if you looked at it from the front, but no other direction. What happens in a Harry Potter cloak, that's right, metamaterial, is that the material has a lattice of molecules which act like lots of these mirrors, where the spacing between the molecules is about the same order as that of light, and can do all this for you, so it can actually move the light around you and sort of render you invisible. This is kind of early days, but I think proper invisibility cloaks are not very, very far away. We might be seeing them, things that you might be able to put on in the next 10 or so years. So watch this space, and I'll be able to deliver this lecture, and you won't be able to see me. Okay, I shall whiz through this one to get on to my last humble, but in fact most important technology material ever, I believe, which is paper. Paper was invented, we believe, by the Chinese several thousand years ago. It is the one material which has probably done more to change human civilization than anything. If you think about it, without paper, we wouldn't have rapid communication, we wouldn't have the printing press, we wouldn't have books, we wouldn't really have anything. Paper has changed human civilization probably more than any material I can think of. And will continue to do so. One of my other jobs is I'm Professor of Maths at the Royal Institution. The the Royal Institution has records dating back hundreds of years. It would quite like its records to go on for a few more hundred years. No electronic means of storing material will be still working in a few hundred years. Things change so rapidly, but paper still will be. So it still makes a lot of sense to put all your records onto paper. Paper is manufactured by essentially taking wood, pulping it, adding water, and doing various other things to it. And this, as I say, is a process which goes back, we think, to the Chinese. And one of the things that you can do with paper, which has transformed my own life and that of many other mathematicians, is, of course, you can do mathematics on it. Okay. I hope at least one member of the audience will be able to work out who wrote that. Anyone know? Well, this is one of the notebooks of Leonhard Euler, where he's looking at topology over here, some of his topology. So without paper, you can't do maths. I know Archimedes wrote in the sand, but he was a genius. I need paper in order to be able to do this. One of my favourite examples of paper, of course, is A4. And A4 has a mathematical property which is very nice, that if you fold it in half, you get A5, which has the same proportions. If you fold it in half, you get A6, which has the same proportions. If you fold it in half, you get A7, which has the same proportions, and so on. Every time you fold a piece of A paper in half, you get a piece of paper with exactly the same proportions. There's only one shape that will do that. If x is the longest side of the paper, x has to satisfy the equation x over 1, if 1 is the shortest side, is 1 over x over 2, which is 2 over x, which means that x is root 2 is 1.41421356237309504888, ... or root 2, and A4 paper has that wonderful mathematical proportion. What else can you do with paper? Well, you can fold it. We saw folded rocks. Folding paper goes back to the Japanese for many hundreds of years. The Japanese art of origami, I'm pleased to say, has now been taken over by mathematicians. This is Robert Lang, one of my favourite mathematicians in the world, who is a mathematician, an origamiist, who realizes that in order to understand the sort of shapes that you can get with origami, you think of mathematically how can you get to those from a sheet of paper and try to solve the geometrical problems associated with that. And Robert has managed to combine mathematics with great art and geometry to take a piece of paper, which is a material, and turn it into wonderful art. And here we have one of his creations. Go onto his website, it's just amazing, which is the bull moose. And if you unfold that and see the paper, that is Robert's design. And my thing to you says, spot the maths. Anyone that looks at that, again, when you saw my pictures of Millock, I got so excited. This is just Millock on a piece of paper. Lovely, lovely folds. And that's all done by maths, and it produced that. Isn't that just amazing? So I think that maths and materials are really bringing art and science totally together. Okay, so I promised I'd finish the lecture 34 seconds early. Does anyone know why? It's Pi Day. So according to the clock in front of me, I'm just about ready to reveal why. So today is the 14th of March, which is in American language 3:14. By finishing 34 seconds early, I finish at the time 3:14, 1:59 and 26 seconds, which is pi. Of course, we've got those extra bits as well. And with those 34 seconds to go, thank you very much.